Welcome to this morning's webinar. We'll be talking about stator end winding vibrations. And this presentation was actually given at PowerGen International at 2013. But what I would like to do is use it as a platform to introduce to you the company and then explain to you more details about the stator end winding problem. And at the end, I will be showing you what other problems we are trying to solve, and maybe it will be of they will be of your interest. Now, the format of this webinar is that the audience are muted, and so I would welcome any feedback or question. Please use the chat box that you might see, and then you can write down your question. Cheska is standing by to help me capture this feedback, and I will be providing some answer for you offline. So today we will not have an online question and answer. So let's begin. So today's agenda is that we will give you a brief presentation on our company. QPS is actually been involved with fiber optics for a long time. We came from the telecom industry, and as a matter of fact, we were in volume manufacturing of fiber grating, making critical components that enable fiber optics communication. Now, we learn about the benefit of fiber optics, and we feel that it is ideally suited to solve a problem in the power industry where there are high voltages and strong electromagnetic field. As a matter of fact, in order to adapt to the problem of the power industry, we selected the problem of stator end winding. And I refer you to the latest preliminary technical specification that is being prepared, and this is the IEC 60034-32. It is a very comprehensive document and talking about the history of the SEW problem and how the industry attempt to solve them. And the main theme of this talk will be on how QPS and AEP work together and to analyze the trending of this stator end winding vibration. Actually, fiber optic is this latest solution that seems to have solved all the outstanding issues historically. In early days, this stator end winding problem was solved using piezoelectric sensors. And piezoelectric sensors have conducting parts, and that raised the concern about causing partial discharge. And so it requires shielding. And this has been a problem that we still have to deal with. Now, there is also electro-optic solution, and the electro-optic solution involve direct conversion from the optical to electrical signal right at the connector, and it will be the electrical signal through a long cable leading to the interrogation unit sitting in the control room. By the way, the connector developed is also contain the signal conditioner. So that is an improvement forward. What we have today, though, is the latest solution using fiber optics. Some of the benefits are quite clear. One, there is no conducting part, so there is no fear of inducing partial discharge, and it is inherently immune to high voltages and the strong electromagnetic field. Other advantages of the fiber optics are also coming with the structure of the device. One is used for telecom, where it's obliged to have 25 years of life, and the other thing is you can always use the strength of fiber optics and the ability to carry the signal over a long distance without suffering from electrical pickup. So the low loss feature, which means that you can keep the signal in optical form and bring it to even a couple of kilometers away in the well-behaved control room, where it's converted into electrical signals. But how did we achieve that? I would like to explain a little bit about what was involved. So in this webinar, we will be talking about our cooperation with AEP, American Electric Power, and we installed our solution called the TG Guard at the Henry Perky plant in Marshall, Texas. And shown here is a picture of the plant. Now, the particular generator involved is a large one. It's built by Westinghouse, about 34 years old, and is about 780 megawatt. And since it is a very large coal-fired generator, and it needs to be hydrogen cooled. By the way, we all realize that because of climate change effects and coal-fire generation is no longer preferred. In fact, the availability of shale gas caused a lot of utility company to switch to gas. However, the problem of stator end winding vibration is still there. So it is important that we pay attention to this problem. This seems to be a crisis-oriented case. Around 2009, AEP, the Perky plant, suffered a ground fault trip, and subsequently they open up the machine and have a crawl-through inspection, and they notice that the machine suffered from damaged top connection at coil 16. And there are plenty of evidence of looseness between all the coils, and you can look at it in the support block. And there are copper debris found at the end winding, and the coil at the top coils have signs of moving. Now, AEP proceed to do a bump test around the area and found top coil 15 actually had a resonance very close to the 2 times line frequency. It covers the span of 115 to 135. So it is a kind of sensitive. Now, so corrective action has been made, but what AEP wants to assure is that this problem would not occur again. By the way, this is some pictures showing you the damaged connection, and you can see that the insulation has all been burned, And now the next slide will show you the actual damaged header cap. Okay. So that header was rebuilt and reworked, and you can see on the left, and versus the one that is damaged. So quite a bit of severe damage has occurred. Now we are interested in talking a little bit about the stator end winding vibration SEW. Okay, so where did it come from? It is from the inherent structure of the machine. In fact, it occurs in all rotating machine, whether it's a generator or a large industrial motor. There is a rotating part called the rotor, and there is a stationary part which interact with it. There is an air gap. Magnetic forces are interacting between the rotor and the stator. And let's say that there is any bit of misalignment, so the air gap might or might not be uniform, so the forces are not balanced throughout the rotation. For a two-pole generator, and the rotor will pass through the stator twice. So it generates a vibration which is fundamentally 2 times line frequency. And the slide show you that if you have a 50 hertz system, then this 2 times line frequency will be 100 hertz. And let's say in the Perky plant, which is running at 60 hertz line frequency, this particular SEW signal is 120 hertz. So this is a problem, and the problem of SEW will be aggravated as the generator age, and due to temperature cycling, loading differences, and all the parts, all the blocking, all the support might suffer from looseness. And this looseness become a vicious cycle. The looser the structure becomes, then the more there's vibration, and stronger the magnitude, and stronger magnitude vibration will introduce more looseness. So how do we monitor this? Okay, this webinar particularly talks about an innovation that came from QPS. It's called the Vibra fiber. And what it is a fiber grating interferometer. And shown pictorially is the model. There are two identical matching fiber black grating and separated at a distance. And this distance, we call it cavity. As you couple laser light into the fiber, the laser light hit the mirror, and every time when there is an index change, there is some reflection. When the laser light hit the second mirror, this reflection change in 180 degree in phase and coexist with any fresh source of laser light. The two sources of laser light set up an interference pattern, which you can see in the graph in the bottom. And the relationship is that the larger the cavity length, the denser will be the fringe, or correspondingly, the bandwidth of the fringe will be narrower. So this interferometer had managed to reduce the bandwidth of the grating structure. As you can see, the envelope shown here is the original grating, and upon the interference, it forms interference fringes which are much steeper and narrower. typically, let's say this cavity length is somewhere between 10 millimeter or 20 millimeter, and that will provide a bandwidth of the fringe of 40 to 80 picometers, which is quite sharp. Now, to work around the fringe area, one would pick one of the fringe. Usually we take the largest, highest magnitude fringe, which is usually in the center of the FBG spectral response. And shown here is a kind of enlarged diagram to explain how the device works. By the way, Vibra fiber is not a standalone sensor. What it is a laser control solution. So we use the DFB laser to launch the light into the cavity, and then the laser is under temperature as well as laser current control, which we call PID. And this PID allows us to place an operating point anywhere we want. And in this particular case, we place the operating point at the rising slope of one of the fringe. And then upon vibration, which move the fringe left and right, and so we will be creating a rising, the operating point is basically moving up and down a slope because the laser is staying put, but the vibration causes it to take a path along the rising slope of the fringe. So this has the advantage of turning optical signal with wavelength change to a optical intensity change, in here shown as a sinusoidal curve, which then can be converted right away into voltage changes. In order to increase the sensitivity of the sensor, we have developed a mechanical amplifier. And this comes in the form of a diving board made with polyamide sheets, and several layers of it sandwich the fiber optics. So this diving board not only protects the sensor head, it also provides the extra mechanical amplifications. As the vibration occur, let's say in a radial manner, this diving board will be under strain, cyclic strain, relaxation, and tightening. So in that case, this is the very action that caused the fringe to move from left to right. Now, in our package design, we made a hermetic seal. There is a packaging cover made with polycarbonate because inside the generator we have to be prepared to have the running temperature up to 150 degrees C. So that forms the guts of our sensor. And by the way, the sensor is not that large. It is 7 by 25 by 38 millimeter, as you can see. The dark casing shows you the color of the polycarbonate material. So when we characterize this SEW sensor, I like to explain to you that there is a lot of design flexibilities. The shape and the form of the diving board can control the resonance frequency. of this sensor structure. For the SEW, since the main signal is around 2 times line frequency, so we designed the diving board so that it has a resonance of about 600 to 700 hertz, and I point your attention to the fact that um, the spectrum is made so that it's relatively flat, and so this is very important. You must have a sensor that will not provide some additional harmonics, because you need to interpret um, the the problem associated with your generator, and I will explain a little bit when we come out with the trending of the vibration. So another thing that you must make certain is to make sure the sensor is linear. And in here, we are using a shaker to characterize it. So the shaker giving a very pure frequency signal. So when we scan across the various frequency, we can clearly see there is only one resonance at 700 hertz. So by keeping the frequency at 100 hertz, and then changing the amplitude of the shaker, we now can measure the linearity of the vibration sensor, and you notice that it is 99.95. Okay. So typically, you install these sensor on the end winding, and because different generator have different structures, and some of them have end caps where they can have clear direction for radial and tangential vibration. In this case, in the Westinghouse generator, the end winding actually comes in a cylinder, and I think you can see it later on in a few slides. And one thing that I did not mention, at that time, we were only monitoring SEW vibration, but since that time, we have developed the sensor into a dual function sensor, measuring both temperature and vibration. It was pointed out that the resonance frequency of the end winding structure is depending on temperature. The temperature of the generator may be operating all the way up to 85 to 100 degrees. So sometimes people measure on the bump test at room temperature and get a value, but in operation, this resonance might go down by 10 to 20 hertz. So this is something that we should pay attention to. So in this case, we did not independently choose the location where we put the sensor. We consult the customer, AEP, and then be guided by what they want to do. And clearly, since earlier inspection showed that they have a problem of looseness in the turbine end, and they saw a lot of dusting. They have the damage of copper debris. So we decided to help them put a lot of sensors on the concerned area. And so the coil T16, which is where it was damaged, we have a dedicated sensor there. And also in T15, when they do the bump test, they found the resonance getting close to 120 hertz. Of course, thereupon they reinforced the blocking, and subsequent data will show you that yes, it did improve. Besides, T15, T14 also show a very weak resonance. So these are the sensitive areas that the customer want to monitor. And then we place two sets of two sensors on the corresponding windings in phase A and B. So we have placed basically 7 sensors on the turbine end. So shown here is part of the channel assignment. This, the software, the user interface of the operating software called the TG Guard can assign channel number to the coil location. So in this case, you see the problem of T16 is channel 6, and then T15 with a weaker resonance, a strong resonance is channel 5, and then we place also one at T14 shown here. Now the other sensor are placed here. I will be referring to this as I analyze the data later on to show you. So a little slide to show you how we managed to install the sensor at the end winding. I mentioned before that this is a cylindrical in structure, and whereas our sensors are rectilinear. So how do we make it couple? And basically is we use silicon cloth, fiberglass cloth, and then soak it in resin and use a clamp to put it together. Now, so when the resin cure, it become a whole block along with the sensor coupling to the end winding as a complete structure. It couples extremely well. Now, the problem of doing that is that it takes 8 hours for the resin to cure, but it did a very good job. So prior inspection, we didn't see any looseness in the exciter end. So AEP has instructed us to place the 6 sensors along some of the location which is evenly distributed. And the exciter end never show any sign of looseness. So this slide shows that after the sensor have been installed in the exciter end, and then actually we wrap them, we wrap fiberglass cloth around it and then paint around it. So essentially at the end, nobody can see there has been some sensors installed. So it's working seamlessly. So these sensors are now giving the signal, and the time domain frequency response also shown as FFT here. I like to comment a little bit about this. Now, clearly, the main vibration signal is the 2 times line frequency. So we are capturing the right signal, which is stator end winding vibration. However, I like to point out to you that there are subharmonics. And in fact, the subharmonics can go down to, for example, 60 hertz. 60 hertz, by the way, is an indication that there might be some rotor vibration being transmitted through the bearing into the end winding. Now, the other thing I like to point out to you is that there's harmonics shown from the 2 times line frequency at 240 hertz. Now, however, this vibration amplitude is extremely small. So what we are saying is there is still some indication of looseness, but it is not alarming. So a waterfall plot indicates over a period how consistent these signals are. And you can see the 2 times line, very clear, and then 240. There is a tiny trace of harmonics. All these are as a result of indicating looseness. So we now would like to discuss some of the monitoring result, the trending results. And basically, since earlier inspection showed most of the trouble in the turbine end, and so we look at the signal and do a little correlation. And so the blocking improvement that we did on T16 managed to improve it a little bit. In fact, if you look at all the channels, referring to channel 8, 7, and 6, and these are T42, T41, and T16. And they are still showing some vibration, but the peak-to-peak amplitude is well within the tolerance. Now, then on the exciter end, channel 11 and 12, which are showing T1 and T4, there is some magnitude of vibration, but they are within the 4 mil alert limit. Here we show the actual peak-to-peak amplitude distribution of all the channels. And this one refers to the turbine end. And again, I point out before that channel 8, 7, and 6 are of interest. Okay, and what I want to point out is that you can see that the vibration amplitude of the end winding is dependent on load. So look at this daily load. There is the generator is running as a base load, but there are load differences at different times. So you can pretty much tell the cycling of the generator operations. Now, the other distribution of amplitude, actually, we show it this way. It's hard to interpret. And as an improvement, what we would like to do is to provide an orbit plot where the vibration magnitude can be distributed exactly where they were installed, and then you can see the distortion and the vibration node. And that will be done as we improve our webinar. Now, you notice that on the exciter end, in general, the peak-to-peak amplitude is less, and it is consistent with the inspection we performed before. And all these are showing you that the peak-to-peak value is much less than a 2 mil, which we consider to be a threshold. And again, across the whole end winding structure, different sensor shows slightly different peak-to-peak amplitude. So this is consistent with the node concept that there is a global vibration pattern, and there are local vibration pattern at the end winding. Our conclusion is that vibration amplitude seems to be reasonable, okay, and then it is clearly dependent on load. Now, from the technical specification that is being prepared, we understand that it is important to relate this vibration with, for example, temperature and also load, and all these things, for example, stator current and all these operating parameters. So today, what we show is the preliminary, the most basic. But what will help the customer is the ability to relate these to their operating condition, and then from these they can derive better diagnostic values. But in general, our mandate working with AEP is to assure them that the generator is working properly. So this is therefore the result. So we think that the generator is operating safely. However, we also show that there are some signs of looseness, and these are shown in T41 and T42. The 16 that has been improved by making steeper blocking, slightly improved, but it is still something we should keep our eyes on. And for the same reason, on the exciter end, there are two sensors showing slightly higher vibration than other location. So, but in general, all these data show that the vibration peak-to-peak value are well within the 2 mil limit, and which we set as a baseline value. By the way, SCW is something inherent in the rotating machine, and there is nothing you can do to completely remove it, but it is advisable that you perform an online monitoring and keeping an eye on as an indication of looseness. What happened is that if you have the ability to determine whether their structures are loose or not, you can have a much less expensive way of making it better. For example, you can re-wedge it and improve the blocking and the support, and to minimize the damage done by this vibration. The vibration, by the way, can cause actual degradation of the insulation layer. And I'm sure that the problem that was discovered by the ground fault trip was due to the excessive vibration, which by now is much better. So we assure AEP that the Perky generator is running within specification now, is quite safe. So this kind of wraps up the story about how QPS and AEP work together. But I want to use this as a platform where we introduce you to our company, and then to show you what we're interested in doing to extend our technology into other important areas. You know about the vibro fiber. We show you the diving board, how the sensor can monitor stator end winding vibration very well. We have since developed a, uh, a, um, a long gauge sensor. And this long gauge sensor is a adaptation of the cavity vibration sensing structure that I cover in this presentation. Um, there will be more information about it, and this long gauge sensor uh, basically can allow you to make a vibration sensor that is 2 millimeters thick, and it can be as long as where your windings are. So you have the options of placing this long gauge sensor in the very narrow gap inside the slot, and you can now measure in-slot vibration. And that has been most difficult to do because nobody makes a sensor that thin that can fit. But now we will be able to show you such a sensor exists. And of course, we need to work with partners to prove that this is working well and then providing value and benefit. Now, one important area that we discover would be to monitor the vibration inside a transformer. Um, the transformer winding can get disturbed when you have a lightning event, when high current surge through the grid and then physically move the coil. However, once the coil has been moved, there is no force to recover it to the original shape. So uh, this introduced a enhanced vibration which we can monitor. And so we uh, in fact what we want to do is to report a few tests in the EIC, which is the Electrical Insulation Conference of next year in June 2016. And by the way, this conference will be held in Montreal. Now, simultaneously, if you were to apply this sensor to the generator, this will be a good idea to do to guard against vibration sparking. And it has been shown that in air-cooled generators, vibration sparking can be a problem. This is a situation where the conducting paint, carbon paint, over the insulating layer on the winding, due to vibration, lost contact to ground, and then momentarily have high voltage and causing discharge. And this cause destruction, and the high voltage will form a plasma, and the plasma will implode and forming a little electro etch, etching the carbon paint and etching even the insulating layer. So this problem, if not corrected, can occur within the first 5 years. So it is of concern to both the user and the OEM. Now, I mentioned before that the world seems to be converting to gas because gas is cheaper and it provides less pollution, slightly less pollution. So, but since gas turbines are smaller and then higher current density were operating, and so people are starting to be concerned about hotspots. These hotspots were due to eddy current introduced via damages when they stick the laminated steel plate together, forming the core. So there exist methods to identify them, but these are very expensive, cumbersome, and uses thermal imaging. When you introduce a magnetic field, you physically seeing the eddy current causing the temperature rise. So again, we use another adaptation of the cavity, and we now have a means of measuring hotspot and identifying which winding has it. Now, continuing effort will be to provide you an array of phase shift rating. This phase shift rating will allow you to measure the actual temperature and locate where the hotspots are within the winding, but that will be a second step. So another potential area that we want to go into is balance of plant applications. Let's say if you have a large motor running cooling water in your power plant, and the traditional condition monitoring solution is to place a piezoelectric vibration sensor, a accelerometer, on the bearing housing. And in our conversation with some customer, in fact, who are very conservative in the design, and they would, for example, keep 3 large motors and 2 running at half load and leaving the third one as a spare. That did not help them in having failure. In fact, the condition monitoring solution that they have never showed them the winding problem. And in fact, whenever the motor failed, upon failure analysis, it was always the winding that is causing the problem. So this is a short webinar, and I'm sure that you have a lot of questions, and so I place my contact information on the screen. And as I mentioned before, you have the option of raising these questions on the chat box. Today, I will not be able to provide a real-time question and answer response, but I promise you, for every question that you raise, I will follow up very shortly. So you can either call me or you can Skype me at Peter Kang QPS. So I thank you again for your attention, and I look forward to hearing from you, and I welcome you if you can join us at next year's EIC, and we will have more things to discuss. Thank you very much.